Okay, so this is our lecture on Chapter 2 material. Before I start, I know that there's a lot of formulas that are presented in this chapter, so I wanted to just go through those that I'll hold you responsible for on homework and the exam, and also just to go through the learning outcomes for this chapter as well. So I'm actually looking on page 91 in your text to give you this information. So underneath key equations, the ones that you do need to know are relationship between wavelength and frequency. So that's the first one listed. You do not need to know how to use the Balmer-Rydberg equation, so you can cross it off your list. You do need to know how to use Planck's postulate on the relationship between energy, frequency, and wavelength, so it's the third one listed. You do also need to know de Broglie's hypothesis relating wavelength, mass, and velocity. Lastly, you also need to know Heisenberg's uncertainty principle. So those are the four key equations from this chapter to know. There are more listed throughout the chapter, but those are the four that you need to know. So again, those are listed on page 91. The one to take out would be the Balmer-Rydberg equation. And likewise on the learning outcomes, all of them are things that you should know and be able to do, again with the exception of using the Balmer-Rydberg equation to calculate atomic line spectra. I'll not ask you to be able to do that. But the rest of the learning outcomes we will go through. So let us start at the beginning here. I will just say that this particular chapter in the text is set out to give you a bit of an overview of scientific discovery and how experiments lead to our understanding of the nature and structure of atoms. So you will see as we go through that there will be some theories that are then rejected later on because they found further information and evidence, and that's quite common in scientific research. We commonly will find information, propose some model or theory to explain that, and then get more information later on and need to modify the theory that we had or come up with a new one altogether. So keep in mind that this is a sort of actual representation of how this work is done, and I will tell you that there's one point at which I will ask you to understand discovery and then sort of forget that you know it in order to fully comprehend what we now know about the electronic structure of atoms. So let's start. The first thing that we'll talk about just is a little bit about energy and electromagnetic spectrum, because that's where the beginning parts of these experiments come from. So we know that different forms of energy make up the electromagnetic spectrum. You've probably seen this at some point in a science class somewhere. We know that we can represent that energy by characteristics of wavelength, frequency, and amplitude. Here you can see that electromagnetic spectrum and then also the visible spectrum down below. I'm not going to ask you to know wavelengths of different types here, but just again to kind of refresh your memory of what we're talking about here in terms of different energies. Obviously frequency and wavelength are the characteristics that we'll talk about in terms of defining atoms and their atomic spectra. So this is just a little review here. So what we mean by these terms: wavelength is the distance between successive wave peaks. Frequency is the number of waves that pass a given point in a unit of time. And amplitude is essentially height of the wave. We won't talk much about amplitude, mostly wavelength and frequency. So you can see down below, we know that particular light, so here you're seeing violet, or here is showing violet light and infrared radiation, and they have different wavelengths. They also have different frequencies associated with them. So one of the first calculations here to be able to do is to compute a wavelength given a frequency and vice versa. It's a fairly straightforward formula that uses the speed of light to interconvert between those two. Speed of light is 3 times 10 to the 8th meters per second. This would be a formula and a constant to make sure that you have written down on your sheet for the exam. The formula is the frequency is equal to the speed of light over the wavelength. Obviously you can reconfigure that to solve for whatever unknown you're looking for. And here's an example of a type of problem using this. So the light blue glow given off by Mercury street lamps has a wavelength of 436 nanometers. What's its frequency in hertz? And so you can see the calculation here. Hertz is the same thing as per second. So if you notice on the bottom, the calculation comes out 6.88 times 10 to the 14th seconds to the minus 1, which essentially means per second. That's one way to measure frequency. So you're essentially asking, per unit time, is what you're looking at there. You can also represent that as hertz. And that's the symbol Hz is hertz. So we talk about this spectrum and the wavelength and frequency here in order to be able to talk a little bit about how the electronic structure of atoms were discovered. And one of the first things that was discovered is that hydrogen atoms in particular, when you excited those hydrogen atoms, they emitted different wavelengths of light. And this was then known to be what are called a line spectrum. This is the light that's emitted by an excited atom, and it was seen that atoms of different elements had different line spectra. And so you can see an example here, the spectra for sodium atom, consisting of the visible line spectrum anyway, of 2 yellow lines, and hydrogen atom having 4 lines here. And so this information then led scientists to try to figure out why they were seeing those particular line spectra, what the light was coming from, and how to learn more about the atom from that information. So one of the first scientists to take a look at this was Johann Balmer. In 1885, he came up with a mathematical relationship that helped explain those lines, visible lines in the atomic spectra for hydrogen. And then Rydberg later modified that equation to fit every line in the entire spectrum of hydrogen. So this is outside of the visible region. They saw other emissions as well, and so this equation helped to explain the rest of those lines that they saw in hydrogen. And so just to sort of at that point they were only looking at hydrogen. Later on, you'll see that it doesn't really explain the other atoms that spectra, and so that needed some further discovery and further experimentation and formulas that came out of that. Something else that was known about atoms was what's known as the photoelectric effect. This was discovered by Einstein, and he found that if you irradiated a metal surface with light, or irradiation of a metal surface caused electrons to be ejected from that metal, and that the frequency of the light that he used had to be above some threshold value for the particular metal that you were looking for, and that it was that threshold value was different for every metal. So this was just another piece of information that they had at the time when they were trying to learn more about atoms in general. And so from that information, he explained that perhaps that beam of light is behaving like it were a stream of particles. These particles were then called photons, and as having a particle nature, they had a particular energy that was related to their frequency by Planck's postulate. What you're getting at here is sort of two things that were discovered, sort of one right after the other. That is the idea that that light behaves both as a particle and as a wave. So this was one example of the discovery that light behaved like a particle. Obviously, up until that point, they knew a bit about it behaving as a wave and having this wavelength and frequency associated with it. So again, this is one formula that you should know and be able to use. The E is energy, H is Planck's constant, and obviously V is for frequency. So this related the energy of a particular frequency, and what allowed you to actually quantify that amount. And you can see the definition of a quantum. That would be the amount of energy that corresponded to one photon of light. Planck's constant, again, that's a constant that you should write down and have for the exam. So that number, obviously, as a constant, stays the same. And you can put in any frequency to calculate the energy associated with that frequency. One of the interesting things that Einstein also found about this effect is that while there seemed to be this threshold energy level that was needed in order to eject the electrons, once you got above that, if you gave more light or less light, you could see the different number of electrons being ejected. But that there was still that energy threshold regardless of how much light you gave to it. So there was a certain frequency that was needed in order for those electrons to be ejected from the metal. So again, we have this idea of both the wave-like nature and now particle-like nature of light. And the next sort of on the scene was Niels Bohr in 1913, who proposed a model of the atom that had electrons circling the nucleus at specific distances in what looked like orbits, like planetary orbits. This energy level of the orbits were quantized, so that only specific orbits corresponded to energies for the electrons were available. This is the one that I'm going to ask you to look at and then immediately try to put to the back of your mind, as we now know a lot more about the atom and that the electrons do not behave in this way. But this was Bohr's model, so you can see here electrons being in specific orbits around the nucleus. This may be the first way that you saw electrons being portrayed in terms of around atoms. This model, unfortunately, still persists in literature today, but this is not how electrons behave. And we'll talk about how we know that and more about the theory of how we know electrons to position themselves and to move around the nucleus of an atom. So in terms of wave-like properties of matter, de Broglie's hypothesis was next in 1924. He suggested that if light can behave like matter or particles, then perhaps matter could behave in some respects like light. This was another important finding, and the formula that you see here is one to be able to work with. This relates now not only the wavelength, but the frequency. H there is Planck's constant, and the mass of a particular particle, in this case an electron. So you could calculate the wavelength of an electron given its mass and velocity using this equation. Again, as we've done before with problems in terms of answering these types of questions, you're looking for, what is the information that I'm given and what's the unknown and what formula do I have that relates those things together. So that would be the approach that I would take again with problems from this chapter as well. You have a couple of different formulas at your disposal and figure out sort of which one fits the situation that you're given. Okay, so at this point there was a lot of information that was known. In 1926, Schrödinger proposed the quantum mechanical model of the atom, which does focus on those wave-like properties. That's the model that we'll use and describe in more depth, and is the one that describes electrons as being in orbitals, not as orbits around the nucleus. You'll see the difference in a little bit. And Heisenberg in 1927, shortly thereafter, stated that it was impossible to know both the position of an electron and what path it follows. This is known as the Heisenberg uncertainty principle. It doesn't mean that we don't know information about those electrons. It's just that it's impossible to determine both things at the same time. What this actually means is the way that we would determine the position of an electron is to modify it in some way, and so in that case we would change its path. So that's the sort of the gist of why we can't know both things at the same time. So we think of electrons now as being finding these electrons in what are known as orbitals. So I'm going to focus on how we describe those orbitals. They are characterized by essentially 4 parameters, 3 that we'll talk about to begin with, and then a 4th. But the orbitals and shapes and sizes are described by these three by these three quantum numbers, n, l, and m sub l. We'll talk about each in specifics. So the first one is the principal quantum number. This is known as n. It can be a positive integer, so 1, 2, 3, 4, etc. It describes both the size and the energy level of the orbital. So 1 would be a low energy level, 2 would be the next energy level up from that, 3 higher from that. So the lower the number here, the lower the energy level of that particular orbital. They're also commonly called shells, and as I said, as the value of n increases, the energy of the electron increases. Also, the distance of the electron from the nucleus increases. These things are one and the same, so the further that you get from the nucleus, the higher the energy of that associated electron would be. The second quantum number is known as the angular momentum quantum number, symbolized by L. It actually defines the shape of the orbital. So there are n different shapes for orbitals. So if you have a principal quantum number of 1, so n equals 1, then L equals 0. So 0 actually denotes an orbital here. You'll see it in a moment at the bottom. If n equals 2, then you have choices for L of being either 0 or 1. If n equals 3, then choices for L are 0, 1, or 2. So these are commonly known as the subshells. You may have heard of them before as S, P, D, and F. So these are the different types of subshells defined by their shapes. So an L equals 0 denotes an S subshell. L equals 1 is a P subshell. L equals 2 refers to a D subshell, and L equals 3 refers to an F subshell. So again, the principal quantum number tells you the energy level. This angular momentum quantum number tells you the subshell, which also tells you the shape of the orbital. We'll look at those shapes in more specifics in a moment. The third quantum number is the magnetic quantum number, symbolized M with a subscript L. This defines the spatial orientation, so where it lies, for example, along an axis. And there are 2 L plus 1 values for this. And they can have any integral value from -1 to +1. So you can see below here, if L equals 0, then M sub L equals 0. If L equals 1, then M sub L can equal -1, 0, or +1. If L equals 2, then M sub L can equal -2, -1, 0, +1, or +2. And these, again, define how these orbitals are arranged in space. I think this will be more clear when you see some pictures of these in a moment. This table, table 2.2 in your text, it's on page 73, I think is a nice way of summarizing these quantum numbers. I know for most of you, you've probably maybe heard of the shells or subshells, but not the quantum numbers and how they relate. So this shows you, you can see n on the far left, so that principal quantum number, 1, 2, 3, and 4, those indicating the energy levels. The L is going to tell you what subshell you have. So notice when n equals 1 and L equals 0, the only orbital we have available is S. It's the 1s orbital, the 1 coming from n. So if you notice next, where n equals 2, the orbitals there are 2s and 2p. If you look at n equals 3, you have 3s, 3p, and 3d. So the n's tell you the energy level. That's the number in front. The L's tell you the type of orbital available. So 0 is S, 1 is P, 2 is D, 3 is F. So notice if you look at n equals 4, you have 4S, 4P, 4D, and 4F. And those correspond to the L numbers 0, 1, 2, and 3. So the N and L tell you, again, the energy level and the type of orbital that you have. For particular orbitals, or for particular subshells, you have a certain number of orbitals in each subshell. That's the next column you see after where it says orbital notation. So s orbitals have, or s subshells have just one orbital. So 1s has one orbital, 2s has one orbital, 3s has one orbital, etc. The p orbitals, or the p subshell, I should say, have 3 orbitals available. So you can see there 2p has 3, 3p has 3. Any d subshell has 5 orbitals. Any f subshell has 7 orbitals. You'll see in a little bit when we look at these electron configurations for elements how this all comes into play. So I would refer you back to this table after we go through a few of these so you can see how this correlates. What you're looking at here is an example of that. So these are showing those orbitals and their respective energy levels. So at the very bottom is the lowest energy, and and you increase as you go up. So a 1s orbital is the lowest energy. The next energy level up would be 2s. The next energy level from that is 2p. I'm looking at where it says multi-electron atoms. The next up from that is 3s, etc. We'll look more about this in a little bit. The hydrogen, you'll see they're all on the same level. That's just because hydrogen only has one electron. So it's only going to be found in that 1s. So focus on the multi-electron atoms. That's what we're going to be concerning ourselves with for the remainder. So in terms of their shapes, this is showing you an s orbital. In terms of what I'd like you to pick out from this is that an s orbital is spherical in nature. And I should have said this by now, but orbitals and how they relate to our understanding of atoms, orbitals are defined as the most probable place to find an electron. So a 1s orbital is a spherical shape that's actually a mathematical prediction of where we are most likely to find an electron. I know that's sort of conceptually a little difficult to maybe wrap your brain around, but try to think about these as probability spaces or probability shapes. So they are describing to us or showing you where you're most likely to find these electrons. So s orbitals are spherical in shape. Different s orbitals have what are known as nodes. These are places where there's 0 electron probability. I'm not going to focus on those. The most important piece here is to know that s orbitals are spherical in nature. And as we get further, so a 2s orbital is closer to the nucleus than a 3s orbital, and the 3s orbital is closer to the nucleus than a 4s orbital. Okay, so as we increase in energy levels, we get farther and farther from the nucleus. P orbitals. You're looking at 3 p orbitals here. One misconception students often have is they look at, say, that px orbital on the far left and think that's representing 2 orbitals, but it's not. It's 2 lobes of the same orbital. So each p orbital has these 2 lobes of, again, high electron probability, and they can lie along the x-axis, as in the px orbital, the y-axis, as in py, or the z-axis, as in the pz orbital. So there are 3 possible p orbitals, and those 3 possibilities are those lying along the x, y, and z axis. These are D and F. I'm not going to go through all of these, nor will I ask you to reproduce these shapes, other than, again, we're just describing where these electrons are most likely to be found. So these are further from the nucleus, Okay, the last 4th quantum number, I mentioned that there were 4 of them. This relates to how we actually will fill orbitals, and it is the spin quantum number. So it's m sub s. The spin quantum number can have just 2 possibilities, so either a +1 or -1. And this represents the fact that electrons have spin, so they have a tiny magnetic field associated with them, and so they can operate either in sort of a plus or a minus spin direction. And this relates to what's known as the Pauli exclusion principle, which says that no two electrons in an atom can have the same 4 quantum numbers. This means that electrons can have 3 of the same quantum numbers, so n, l, and m sub l, but those 2 electrons have to have opposite spins if they're in the same, in that same orbital. They have to have opposite spins. You'll see in a little bit how that relates to electron configurations, which is one of the main sort of skills to be able to do from this chapter. This relates back to when we were talking about the line spectra and how we see different amounts of light. It was further discovered that you can actually, this is the equation I told you not need to be able to do, but this tells you or describes how they were able to see different wavelengths of light. So what happens is the electrons get excited to different energy levels, and so when they drop back down, they emit different wavelengths of light. So whether they drop, say, from the 5th shell to the 3rd shell, or from the 4th shell to the 1st shell, those would be different wavelengths of light that were emitted. And so lots of information is now known about those specific amounts. And again, this is the relationship that explains that. This is not one that I'll ask that you're able to calculate from. This is an important sort of concept first shown here. We'll come back to this more and more as we look at interactions between atoms. But it's this idea of effective nuclear charge. And it essentially means that as electrons get further and further from the nucleus, they are effectively shielded from the pull of the nucleus to pull it in, or essentially to attract it to the nucleus. So they are essentially shielded from that attraction from the nucleus. So as those outer electrons get further and further from the nucleus, their effective nuclear charge, or the amount of charge they actually feel, is less due to this shielding of the electrons that are in shells below it. And this, as you can imagine, affects how those electrons will interact and react. Okay, so we're building up to actually coming up with electron configurations and orbital diagrams. Some terminology here to help you with that. So an electron configuration describes which orbitals are occupied by electrons. So essentially it describes, if you have an atom with 6 electrons, where are we going to find those electrons? Degenerate orbitals, these are orbitals that have the same energy level. So those 3p orbitals in a particular subshell, so say 3px, 3py, 3pz, those 3 orbitals are degenerate because they're on the same energy level to each other. Ground state electron configuration, this is what I'll ask you to do in most cases. This is the lowest energy configuration. I'll show you how you fill that and do those. And off-bow principle, this is what we use in order to come up with the ground state electron configuration. It's a set of guidelines that we use for how we fill orbitals. What's the filling order that we're going to use? So these are the main rules that you're going to follow, and that's that lower energy orbitals fill before higher energy orbitals. An orbital can only hold 2 electrons, and they have to have opposite spins. That comes from the Pauli exclusion principle. And third, if you have 2 or more degenerate orbitals available, so say px, py, and pz, an electron goes into each until they're half full. And then the electrons will get paired up if you still have electrons left. Those electrons in those half-filled orbitals all have the same value of their spin quantum number. This is known as Hund's rule. This means that when you express them in an orbital diagram, you're going to show them all in the same direction. You'll see that in a minute. So let's go through a few of these. First, we'll do electron configurations, and then I'll show you some orbital diagrams. So here's the electron configuration for hydrogen. Hydrogen has 1 electron. Again, we know number of electrons by looking at atomic number. If it doesn't have a charge, then the atomic number tells us how many electrons it has. So hydrogen has 1. The lowest orbital is a 1s orbital, so it puts 1 electron in that 1s orbital. So the configuration is the energy level is the first number that you see. The type of orbital, here an s orbital is written next, and then the number of electrons in that orbital is written as a superscript right above the orbital itself. So helium has 2 electrons. It's going to go in that first s orbital, and that s orbital would be filled. So its configuration is 1s2. Lithium has 3 electrons, so 2 of them go in the 1s2. The next orbital up from that is a 2s, so that third electron will go in the 2s orbital. Nitrogen has 7 electrons, so it fills the 1s, the 2s, and then those 3 that are left go in the 2p. And you'll see in a moment on an orbital diagram each of those 3 electrons. So one would be in 2px, one would be in 2py, one would be in 2pz. So here's those orbital filling diagrams that I was talking about. So they're shown by just usually a line. Written underneath the line is the orbital, and then the arrows either pointing up or down denote an electron. So you can see for hydrogen, 1 electron in that 1s orbital. Helium has 2 electrons in that 1s orbital, represented by the arrow pointing up and the arrow pointing down. This denotes that they have opposite spins to each other. Lithium, again, so here's filled in its 1s, 2s has 1 electron. And then nitrogen. Now here you see over on the 2p, 3 lines. That represents 2px, 2py, and 2pz orbitals. And you can see that the 1s is filled, the 2s is filled, and that there is 1 electron in each of the 2p orbitals. Note they're all pointing up, as they should be. They all have the same spin, and we put 1 in each available orbital, and then we'll go back and fill them if we had extra electrons, which you'll see in a little bit. Something else to note here, so if we looked at, say, sodium, sodium is atomic number 11, so it has 11 electrons. So its electron configuration 1s2, 2s2, 2p6, so that would then fill the 2p orbital, and then 3s1 follows it. If you look at the noble gas that immediately precedes, or not immediately, noble gas that precedes that element, in this case would be neon, what you see on the right is a shorthand configuration that's commonly used. You are expected to be able to write it both ways. So the full electron configuration on the left, or using the shorthand configuration on the right. Here's one for phosphorus. Again, so the neon represents the 1s2, 2s2, 2p6, because that's neon's configuration. This is only used for the noble gases. So you could use helium, neon, argon, krypton, xenon, radon appropriately, and then whatever else that particular element has after that point. So again, in case of potassium here, you could use the noble gas argon and then 4s1. You can see its full configuration written out, and that's the configuration for argon. So again, it's just a shorthand way that we use to write these configurations. Scandium, another example here. I'm not sure I have it on a slide here, but in your text, just quickly find the page. On page 86 is the orbital entire filling order. It's about halfway down the page. You could either memorize that, or I would suggest just writing it down on your exam sheet, and it will show you what the orbital filling order from 1s all the way through 7p. Okay, so if we go back to the periodic table, you can tell a little bit, or a lot actually, about electron configurations by looking at the periodic table itself. And you can see that they separate out into different areas. If you look, for example, the group 1A and 2A on the far left, you'll notice that all of those elements are filling their s orbitals. If you look in the middle, the orange block, you'll notice that all of those are filling the d orbitals. And what I mean by filling is that they if you look left to right, you'll see it go from 3D1, 3D2, 3D3, etc. If you look at the green block, you can see those are filling p orbitals, and at the bottom, sort of red, orange-red, those are filling their f orbitals. So that's one thing to note, and one thing that can help you here. Another is that if you look at the periods, not marked on this periodic table, but if you look, so period 1, period 2, 3, etc., that tells you the energy level that's being filled. And so, for example, if you look at sodium, so sodium has 1s2, 2s2, 2p6, and it's filling its 3s1. So the period 3 here will tell you the outermost energy level that's being filled in that particular element. If you look at potassium right below, you can see it's filling its 4s. It's in period 4. So that's another relationship there between the electron filling and the periods on the periodic table. One more thing, I guess not noted here, but these are also known as, so the blue are known as the S block elements, the green as the P block, the orange as D, and then the red on the bottom as F, because those are the outermost orbitals that are being filled in each of those cases. There are some anomalous electron configurations. These happen with higher number elements, and the reason that we see these are, it turns out that if you can half fill an orbital, that is a state that's good for an atom. So if you look, for example, here at chromium, you can see that you would expect that configuration to be 4s2, 3d4, where it has a filled s orbital and only 4 in the 3d. And it turns out that it's more stable for that chromium atom to have 2 half-filled orbitals, so a 4s1 that's half-filled and 3d5. Ds can hold up to 10 electrons. So that's the actual configuration we see, because that's the most stable configuration for chromium to have. And so we do see these for some of the higher atomic numbered elements. I will ask when you do electron configurations to just stick with your expected configuration. That's what I'll obviously count as correct. But know that we do see these different configurations for higher numbered elements. Okay, one more sort of main point to take from this chapter, and this will be something we carry forward when we talk about reactions and forming compounds, become very important, and that is what's known as the valence shell and then valence shell electrons. So the valence shell is the outermost shell that atoms of a particular element are filling with electrons. And this is really important because these electrons in their outermost shell are most commonly the ones that are going to interact with other atoms. So there's where the reaction's happening. That's where we get compounds forming. That's where we get electrons being shared or transferred from one to another, are from the valence shell electrons. So they are the ones to really focus on, and the ones that we will spend most of our time talking about, frankly, after this chapter, is valence shell electrons. And it turns out there's a relationship between the group number. Remember I said before in chapter 1 that would come back, and here it is. The group number tells you the number of valence shell electrons. So atoms in group 1A all have 1 valence shell electron. Atoms in group 2A have 2 valence shell electrons. They're in different levels, okay, depending on what period they're in, but they all have 2 valence shell electrons. And I'm going to actually refer them as valence electrons, so I'll sort of drop the shell at this point. Group 3A would have 3 valence electrons, group 4A, 4 valence electrons, etc. Group 8A, 8 valence electrons. You can see a couple of examples over there on the right. So lithium has 2s1, so it has 1 electron in 2s. 2s is its outermost shell, its valence shell. It's in group 2A. I'm sorry, it's in group 1A. And so it has that 1 valence electron. We look at sodium. Sodium is in group 1A. It has 1 valence electron. Chlorine. Chlorine is in group 7A. It has 7 valence electrons, 3s2, 3p5. We look at bromine. Bromine also has 7 valence electrons. It's in group 7. So the main takeaway here is that those group numbers tell us the number of valence shell electrons that we have. And those valence electrons are the ones that are actually going to interact and form compounds and participate in reactions. Oh, here it is. So this is just giving you a very sort of generic view of the periodic table and how the orbitals are filling. So this hopefully helps in terms of visualizing the table that I showed you before, and again showing you that S block, P block, D block, and F block, because those are the orbitals that are being filled, the outermost orbitals being filled in those locations. Electron configurations and valence shell electrons, it's something really to practice. I would just pick at random some atomic numbers and elements and try those electron configurations out. You could just Google electron configuration for any element and find your answer if you need to. Likewise with orbital diagrams, I would practice those as well. Again, just randomly pick something off the periodic table and draw an orbital diagram for it. And again, just Google orbital diagram oxygen, and you'll be able to check your answer that way. So that's what I would recommend in terms of just getting enough practice with that until you feel comfortable doing doing those. The last piece here is just to talk about a concept known as atomic radii, or essentially the size of an atom. And it turns out that there is a relationship between the radius of an atom and its position on the periodic table. There are some trends that we see here. And here they are. So the basic trend is this. As we go down a group, so if we look at, say, group 1A, hydrogen, lithium, sodium, potassium, as we go down a group, atomic radii increase. So from hydrogen to lithium to sodium, each of those atoms increase down to cesium. And the numbers underneath are giving you the atomic radius. The reason for this is there's a number of electrons, a great number of electrons difference between them, and so those are occupying energy levels further away from the nucleus. And so that's why we see the radii increase. You can take any group there. So if you look at, say, group 6, oxygen, sulfur, selenium, again, the trend is the same. So as we go down a group, the radius increases. Something different that we see as we go across a period. So if you look, say, at period 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, the noble gases are not shown in the radius. Anyway, as you go across, you see that the radius decreases. Okay, so the trend as we go across a period, the radius decreases. And you might think that seems odd because we're adding electrons, right? But it turns out that effective nuclear charge that I talked about before comes into play here. So as we increase the number of electrons, their actual effective charge is decreasing because the electrons nearby it are shielding them from the pull of the nucleus. So their radii actually will decrease. So again, trends here is what to know. So as we go down a group, the radius increases. As we go across a period, the radius decreases. And that's the end for this chapter.